अच्छा वो आ गया। हाँ एक बार वापस कर दो। हेलो। तो सबसे पहले आप अमितेश पर अनशेयर कर और शेयर रिकॉर्डिंग अनशेयर कर। हाँ तो क्या कंफ्यूज भी कर नॉट टेकिंग शेयर विद साउंड और वीडियो भी वीडियो हां शेयर।
I request my colleagues within TIFR to come to the lecture theater and listen to the talks. It will be great if you could join us here. Those who are in Zoom.
Nobody. It's impossible. No. Oh, yeah.
No, I think it's okay. Which one? Displayed. Okay. Yeah, it's fine. Yeah, yeah. We are as good as the Wi-Fi's fluctuation. Yeah. Okay, almost there.
Okay, there is some insight. There are lots of really good quality. Good visual and sound. So we have an idea of everything. Okay, so
I think it's time. I welcome everyone via Zoom. I would request whoever is in TIFR and still connected by Zoom, please join us in the lecture theater. And I thank all of you for joining us. Today is a very special Wednesday colloquium. It covers the Nobel Prizes, and this is the 2023 Nobel Prizes in physics, chemistry, physiology / medicine. And as every year, the prizes are going to be given by the 3 prizes. They're going to be represented by TIFR colleagues, faculty members here, experts in their in the fields where the prizes were given. And it's a great pleasure to welcome Amitesh Anand from DBS, Professor G. Ravindra Kumar from DNAP, and Professor Deepa Khushalani from Department of Chemical Sciences, to give the 3 talks. And before we start, I would like that someday we have our own, okay, giving this talk. So don't say no, never say no, okay, never say no, and let's work towards it. So anyway, Amitesh.
Sure. Thanks so much. Sorry. With that spirit, let's start. It's an honor. Thanks, JD, for inviting me to talk about this work, and it's a absolute honor to talk about something that is as good as getting awarded a Nobel Prize. I did it last year also, but last year I was telling Shubha just now that last year I had to really explain what's the real impact of that work, how is that gonna have value in our life. This year, that's not the case. I don't have to justify anything. I don't have to tell you what's the impact of this work. This is transformative in real life. We have seen the changes. I'm injected with the mRNA virus. mRNA vaccine. I'm starting with the and it's good to do it in the beginning, then in the middle of the talk. Cool. So last year, when I was about to wrap up my talk about Fonte's work, I did mention that the one very strong contender for last year's Nobel Prize was none other than Kathleen Carico. And I encouraged all of you to go check out her work. I hope some of you, otherwise I'm here for you. But then JD has a very interesting take on that. He said that probably they didn't award her last year because they wanted to see the impact of it for another 1 year and seeing that is like really valuable. And I understand that can be really the thing. Okay. So better late than never. This year's Nobel Prize has been given to Kathleen and Drew Wiseman, both colleagues for a long time working at UPenn. This year, I think, especially in the category of physiology or medicine, or should I call physiology and medicine because the kind of work it is, there have been lots of talk about these awardees, especially Kathleen. But most of those talks have been about her hardship, her perseverance, her endurance, all in all, her tenure, non-tenure, etc., etc. I have huge respect for that. But in all of that, we have somehow missed talking about the science and the scientific brilliance of theirs. So in today's talk, let's celebrate their science. Let's talk about what they have done and how has that changed the entire vaccinology. And not only that, I'll try impressing you on how it is going to change the other therapeutic areas also. So I believe most my younger colleagues over here would have either not heard of these diseases, or probably just when we go for vaccination, we got to know that, okay, these are something that probably exist and we should care for. But none of them are really, either they are like really, really restricted or they are completely eradicated. I remember during my school time, I used to see cases of polio in front of me, and those things are eradicated almost from everywhere. So that's the reason why 3 things have been said to be transformational for the medicine. And those are very simple things: clean water, sanitation, and of course, vaccine. I'm talking about this particular thing over here, and I'm especially highlighting this thing that till 2020, the record for the fastest development of vaccine was with mumps vaccine. And that vaccine was developed in 4 years. And see the kind of statement is made. It took just 4 years, just 4 years. Now, thing is that this is a mathematical modeling based study. So please don't ask me how all these things have been done. I have better colleagues over here to explain about those things. But the message from here is that what would have happened if vaccine was not there? So this is a modeling to talk about. This black line represents the death that actually happened. And the red line is for what would have happened if vaccine was not there. According to this estimate, just within 2021, there could have been 15 million excess death because of COVID-19. And we are talking about 4 years for mumps vaccine. Of course, there are other ways also to mitigate the spread of COVID-19, and we are well aware of that. But even if we take the most conservative approach, that number is astonishing, and we cannot afford to have that kind of loss. And this is when there were like lots of talk about in fact, I happened to be kind of free around that time. I was finishing my postdoc and I was planning to come here. And for that reason, I appeared on several news channels and all that. And everyone was asking me when the vaccine will arrive. And they were like, why it can't arrive in a month? And so like, we really had to explain the process. And when it actually arrived, then people started asking the other thing around that, has there been any shortcut? Have they taken proper approach of developing vaccine and everything? So thing is like that. So let's talk about the pace of development of this vaccine. This is a scientific miracle. One of the, I'll be a bit satirical and critical over here. One of the rare thing that happened, rare good thing that happened from Chinese science around that time is that on 10th of January 2020, they published the genome sequence of this virus. In fact, the person who published this was banned from his lab for a good amount of time, but they published it. 10th of January 2022 was a Friday. Friday, the genome was released, and we are talking about the next Monday, the vaccine was designed. So that's the pace. That's how these kind of vaccines can be designed. And 24th February of the same year, this was already sent for phase 1 clinical trial. Towards the end of this year, President of the USA received the vaccine. And just 1 month later, common people like me received the vaccine. So it's all just within a year. And of course, that's why there were lots of apprehension. There were lots of doubts that has there been shortcuts and all. Now, the thing is that we do sometimes, but mostly in science, we don't take shortcuts. We do things thoroughly. And I'm going to use a slide in Professor Mohit Jolly's style from ISC on a lighter note. So we talk a lot about application, transformation, whether the science has value or not. But everything that underlies is the fundamentals, whether we know fundamentals or not. And this takes time. And this is what provides us the raw material to build on things and then get value out of it. So let's talk all the way back to when mRNA itself was discovered. There was a time when we knew about protein. Of course, protein is something that we knew for a real long time. Then we knew about DNA. I think that was kind of confusing a lot, and like scientific fraternity was trying to understand why only some portion of DNA is translated into protein, and what dictates is how does this happen. And that's when, again, a lot of basic research, lots of fundamental research went in to prove that there is something called messenger RNA, and its job is to take messages from DNA, depending on the context, depending on the environment, and then go for the translation of the protein that's required in that given condition. Now, this idea that there is an mRNA that can result in translation of a given protein immediately led many scientists to explore the potential of it, whether we can hijack it. Can we now dictate on the cells which protein they have to produce. With that, many of them started to work in this direction. This is from 1989. This is Robert Mellon's. Again, try reading about Robert Mellon. He was a graduate student with Inder Verma. He didn't continue his PhD for multiple different reasons. And the story between these two itself is very, very interesting, very controversial. But then this was the study for the first time where fatty lipid droplets were used to transport mRNA into the cell. We can call Carico's work or Wisman's work as the foundation for the development of mRNA vaccine, but these works are not less than that. What I'm trying to say is that things happen in pieces, and then they all come together to give what we see as a product. In very next year, 1990, from Phillips' group, they actually injected mRNA into a mouse and observed the production of the protein. Now, for this work, Drew Wisman, the co-awardee for this year, actually says that this was a transformative work. But the problem was that the mouse got sick. The mouse got severely sick because these mRNA were resulting in a very high immune response. So that was a huge bottleneck. Of course, the transport of the mRNA into the cell itself is a task, and that's why over here I have listed that the job of messenger is not easy. They have to reach to their desired site, and they have to reach there safely in intact form. And then, of course, they have to avoid being detected by the immune system, and there should not be hyperimmune response. At the same time, it's not only for our body's protection, it's also because if there is a heightened immune response, that will lead to downregulation of the expression of that mRNA. The coding of that protein itself is get reduced, which will compromise the entire purpose of that mRNA. So that, and then of course, while we are working on trying to optimize the reduction in immune system, we also have to optimize a higher expression of that protein. So with all that, here is the landmark work from Carico and Wisman. You're not indicating both time.
No.
Oh, good. So I see. Okay. So, now the prior art that exists, so the information that they had while they were working on it is that bacterial DNA is more immunogenic compared to mammalian DNA. And they had some bit of understanding, and it's all chemistry, it's all chemistry, it's all chemistry. So they knew that mammalian DNA has some modification, and because of that, they are less immunogenic. That information, and then they also had information that bacterial mRNA contains lesser nucleoside modification compared to mammalian mRNA. And then, of course, that's the reason why there are lots of TLRs for mRNA versus, and that exists for DNA. Now, with this prior art, what they wanted to explore is whether these nucleoside modification can have immunostimulatory potential on RNA, or like if they alter these things, can they play around with the immune system stimulation? So let's talk a little bit of their data. So this is where what they've done is that they are looking at the immune stimulation. The marker over here is TNF alpha secretion. I have highlighted these controls over here. So lipofectin is the carrier that they have used. Poly-IC is a synthetic double-stranded RNA. So when they introduce this, they see secretion of TNF alpha. When they use RNAs, that kills the RNA. The secretion goes down. R848 is a known agonist for TLR7 and TLR8, and that's why you see a very high secretion of TNF alpha. Of course, this is a chemical molecule. This is a chemical agonist. This is not an RNA, so that's why RNase does not have effect on it. And then in vitro transcribed RNA has a huge immune stimulation over here, seen as again reflected by TNF alpha secretion. Over here is a panel of RNA from mammalian cells, and you can see that in majority of the cases, this TNF alpha secretion is quite low. Compared to that, if you look at E. coli total RNA, there is again a very high secretion of TNF alpha. Now, another interesting thing, especially from microbiology point of view, is this particular bar. So if you look at mitochondrial RNA, again, there's a high secretion of TNF alpha, which again goes back to, again, the symbiont hypothesis that mitochondria has a huge similarity with bacteria, and that's why it is probably the chemical landscape of RNA in the mitochondria is similar to bacteria, and that's what you see over here. So from this, they were able to state that the immune activation potential is inversely related to the nucleoside modification. So this was a good idea. They went on looking at the actual impact of it. If they can modify the nucleoside, can they really recapture those things? So this is a study, this is the data of, again, from the same study, where they have taken these two synthetic RNA, RNA 730, RNA 1517. These are just the control that they have used. Again, TLR3, TLR7, TLR8, these are the toll-like receptor. These are, again, kind of an indicator for the immune stimulation, immune response. I'm not going too much into the technicality over here. The vector control over here is because the cell that they have used, this is a 293 cell, and they have some endogenous expression of TL3, and in order to ensure that that endogenous TLR3 is not affecting their result, they went on introducing something to prohibit or limit the expression of that. Now over here, what you can see is that compared to unmodified one, these RNA that were having these modified nucleosides were having lesser stimulation of TLR7, TLR8, again reflected by IL-8 level. So nucleoside modification were actually suppressing the immune stimulation. This was the breakthrough the field was looking for. They had good carrier molecules. They had ways to deliver that RNA to the site. They had those delivery system to inject in our body. This was what was a real bottleneck in achieving the therapeutic potential of mRNA. And that's what they get over. I'm going to just talk about one more study, and this is a study for two reasons. One is that there were lots of debate whether the immune suppression that Kariko and Wisman has seen is actually because of nucleoside modification or because of the production process. Because if there is impurity in the RNA preparation, that can also have a different impact on the immune stimulation. So, and the other reason for highlighting this work is, of course, the authors. All of them are from Moderna. Moderna, the one of the two that were responsible for the mRNA vaccine for COVID-19. And the timing is, again, important. They were like, so what I'm just trying to impress upon you over here is that they were working on it for a real long time. They were working on every aspect of it. They were looking at whether they need to have a better preparation process for RNA also. And over here, they have shown that, so they have used hippo mRNA as their system over here. And what you see over here is uridine. Uridine is the canonical nucleoside. And this methyl pseudouridine is the modified nucleoside. And process A and process B, in a very simple way, process B is a more pristine process of forming RNA. They have simply used HPLC-based purification process to remove or limit the impurity to the minimal. And what they see over here is that it's actually both. If there is impurity of double-stranded RNA, that can also have immune stimulation. At the same time, the substitution of uridine to pseudouridine, in this case, methyl pseudouridine, actually was responsible for responsible for bringing down the immune response. With that, they developed this beautiful system where you can encapsulate mRNA into lipid nanoparticle that goes in, get engulfed by endosome. They can come out from endosome safely. Then they can hijack the ribosome for the production of protein. That's again either by MSC class 1, class 1, or over here by class 2 can result in formation of your antibodies. So these are the antibodies that again provide us the protection against this virus. So that, but then again, this mRNA vaccine was not the first of its kind. In fact, back in 2017, when Zika virus infection was spreading, they had claimed that they already have mRNA vaccine that can actually work on it. Only thing is that COVID became a global crisis, and the kind of problem it was, it required all sorts of solution. So mRNA had that beautiful environment in which everyone was ready to accept it. A few things that we should be happy about is that CCMB at Hyderabad has been able to replicate this process. We now have our own mRNA-based vaccine. We have that platform. There is a lot of talk about using mRNA vaccine for the treatment of, or not treatment, vaccination of tuberculosis, against tuberculosis. We know this BCG vaccine and the efficacy of the BCG vaccine is 50%. So take it, not take it, again. So we need better vaccine, and our government right now has this mission to end TB by 2025 or so, although that mission is a bit more ambitious, over-ambitious. But then if we have these kind of things, not in 2025, but sometime soon, we should be able to like really reduce the burden to a good impact, a good number. Now, just quickly, 2 more slides, because I really want to impress that it's not only about vaccine. It is going to transform every other aspect of therapy. The guys who actually developed this vaccine, BioNTech and Moderna, their own interest was not in vaccine. This one is BioNTech. They were working on cancer immunotherapy. They are still working on it. They have now went ahead with their trials and all. So the idea is again simple, that figure out what are the proteins which are unique to those cancers and try developing mRNA against this so that you can train your immune system to selectively target those cancer cells. So that was the idea with which BioNTech was formed, and hopefully sometime soon this will again be a reality. Derek Rossi, the co-founder of Moderna, again, his interest was in a very different. He wanted to bring back pluripotency in differentiated cells. That's what he started with. It's just that when he met with his sponsors and all, and the co-founder, they said that you should look into other applications also, and then he moved into vaccine. Now, of course, COVID triggered all those things. So that, and I really, again, mostly to my younger audience, I request you to read this one. It will hardly take 5-10 minutes. It's a beautiful story about this entire field of mRNA vaccine. Not actually only vaccine, it's all about discovery of mRNA to how it is inching towards transforming medicine. And with that, I really acknowledge JD for giving me this opportunity. And I have missed citing some of the most sources, and that's why I'm acknowledging here as an umbrella. And thank you so much.
Thank you, Amitesh. That was right on time, and I request Deepa to come in. We will take one pressing question. Yeah, from.
Yeah. Hi. I happen to notice that you were talking about mRNA vaccines in both, like, for example, tuberculosis, where the microbe itself has DNA, right? And also in coronavirus, it was an RNA virus, right? The virus. So is there a difference in how mRNA acts in these cases when the thing you're targeting itself has no DNA? And
so in both the cases, mRNA has to pass on the message that what kind of protein they have to form, be it DNA based microbe or RNA based microbe, like in this case COVID versus, as you rightly mentioned, about Mycobacterium tuberculosis. The idea is that the messenger has to pass on the message that they have to make this protein, and that protein is going to get presented by, again, those antigen presenting cells, so that they can start producing the antibodies, which will then target those microbes.
so in coronavirus, there is information RNA, and then there is also messenger RNA.
Messenger, so we hijack that RNA, and that RNA, the same RNA, that RNA, then using mammalian translation machinery, start forming that protein. Yeah.
Okay.
They don't have two systems.
Okay. I have to stop it here. However, he will be back again at the end of all the 3 talks. So please hold on to your questions. Kona, you have a question? So please hold on to your question. And we will start with Deepa. Continue with Deepa, sorry. Continue with Deepa.
Okay. All right. I will start speaking in the interest of time. So thank you, JD. And it's nice to see a crowd. And so let's start talking about chemistry. Nobel Prize in Chemistry, and the title that I've given is Tiny Seeds for Big Application. Hopefully, as we go along, you will try and sort of appreciate what I mean, how tiny is tiny and how big is big. And so if it's okay with, so let me start off with actually, I need everyone to have a certain baseline information before we get started talking about the actual research that this Nobel Prize is focused on. And the main concept that I need everyone to realize is, first of all, we'll be talking about solids. The Nobel Prize is based on working with solids, especially semiconductors. There are other kinds of solids, things like metals and insulators, topological insulators, alloys, and so forth, that also show very interesting behavior. But today's talk, this year's Nobel Prize is restricted to semiconductors. So keep that in mind as we move forward. I'll try and explain for those of you who don't know what semiconductors are. These are the people, the conventional 3 white men that get a Nobel Prize. And the citation is for the discovery and synthesis of quantum dots. So discovery and synthesis. So the word synthesis is in, that's why it's in chemistry. These are the 3 people. And we'll discuss their work, but like I said, I want some baseline work understanding. So one is that we're working with semiconductors. We're going to be talking about solids. And the other aspect I need everyone to be sort of completely aware of is that when you change the size of these structures, when you go from what is called a bulk length scale down to a small length scale, and small is in quotation marks, you are altering the properties. You're altering a variety of physical and chemical properties. Now, this doesn't mean that I'm going from a centimeter down to a millimeter and everything happens. No, it's below a certain critical threshold radius where you suddenly start seeing phenomenal behavior of materials. All right. That's one aspect. The other aspect I need you to realize is, so by the way, what are the properties that we manipulate? We can manipulate a simple thing like melting point, and this is without changing the chemical stoichiometry. So you do not have to span the entire periodic table trying to find materials that melt at different temperatures. The same material can melt at different temperatures by changing its size. Another thing you can change is something called a redox potential. This is huge in catalysis because the ability to oxidize and reduce is important. So when you change the size, you change the redox potential. You can change other things, phase transformations and so forth. But the thing that most interested people is the fact that you can change the electronic properties of these materials when you go on a smaller length scale. The electronic, what do I mean by the electronic properties? I mean the way the electron is behaving inside this semiconductor. I'm changing L, L being the dimension, the size in which this electron is sitting. You know, think of a particle in a box for those of you familiar with quantum mechanics. And what I'm changing is the size of the dimension, this L dimension. And the wave properties of this electron get manipulated. The allowed eigenstates get changed, okay? And for example, the band gap of your semiconductor scales with 1 over L squared. What does that mean? When you change L, you increase the band gap. When you increase the band gap, you change the absorption capability and the emission capability of the semiconductor. Physically, the way the material looks, the color that it has. In addition, you get discrete states. It starts looking almost like an artificial atom. These words are used when you're changing the particle size. You're not making single atoms. These are clusters of atoms. We're talking about tens and hundreds of atoms, but you're having discrete energy levels, both in the valence band and the conduction band. It's no longer a continuum. So lots of interesting things going on. How do we know all this? This we've known for a long time. This is not done by the current Nobel Prize winners. This has been done in terms of models, in terms of mathematical calculations, in terms of theory by a variety of scientists going back a century, at least from what I was able to read. Okay, and a variety of scientists' names crop up here. But what the issue is, getting experimental proof to validate their theories. That was the issue. Like I said, this has been going on for a long time, but the ability to experimentally say, yes, this theory is correct. Yes, if you make a quantum size structure, you will have unusual electronic properties was turning out to be a bit of a challenge. By the way, you don't only need to change dimensions in 3 dimensions. 3 dimensions is the quantum dot that you see there. As long as you restrict the size and you go into what is below critical dimension in one of the XYZ directions, then you can in principle create what is called a quantum structure, and you can create quantum wells and quantum wires. So when it came to creating experimental proof for these theories that lots of famous scientists came up with, people started working with fabrication of very precise small dimension structures. Now, if you think about what I mean by precise, you need homogeneity. And what is the size we're dealing with? I'm talking on an order of few nanometers, 1 nanometer, 5 nanometers, 10 nanometers, nothing on a large length scale. On that length scale, we're talking about a few hundreds of atoms. You need to be able to create a semiconductor in a homogeneous way on that length scale. So what are the ways that engineers and physicists were doing? They were using techniques such as this. This is called MBE. It's one of a large workhorse. And this has been well established. This started in late 60s and 70s and so forth. And this allows you to create very nice, what are called quantum well structures, those one sort of thin films of these materials, all right? But they are grown on a substrate. And for what it's worth, like I said, the science is not new. In fact, a Nobel Prize was given, again, to 3 lovely white men about 20 years ago. So question is, theories are there. People are sort of fabricating structures, in this case, quantum wells. So what is the issue? The issue is that there is no large-scale way of making quantum-based structures for other kinds of applications. These Nobel Prizes were for integrated circuits, microelectronics, and so forth, and fantastic materials, don't get me wrong, fantastic devices, but in terms of cost effectiveness, applications, there was a deficiency. So this is what the Nobel Committee, in fact, wrote in one of their documents, and I've underlined it here. The predictions pioneered by various scientists, such as Froelich, that small particles should have size-dependent material properties were not yet accessible to the experimental test, okay? So this is where the 3 scientists who won the Nobel Prize come in. So I'm going to start off with this person. His name is Alexei Yakimov. So Jyotishman, give me a 5-minute warning. I'm running a little behind schedule. So he's Russian. He did his work entirely in Russia. He got educated in Russia. He did his work in Russia. And he published his paper in a Russian journal that basically the other 2 participants did not see, right? So it was hidden from you, but suffice it to say there was enough very impressive stuff in that article that got him the Nobel Prize. This work was done in the Vavilov State Optical Institute. So what was he working on? He was working on something called doped glasses. It's been known for a long time that if you put certain kinds of elements inside a melt of glass, okay, you take glass, you melt it, or you take a precursor of glass, some form of silicon oxide, you melt it, and then you sprinkle in a few species, things like cadmium or sulfur and selenium and so forth, and then you anneal and sinter this melt and make a glass out of it, you will find that you can change the color of the glass, okay? Glass blowers in whatever many centuries ago knew how to do that. They did not understand the science. And this was well sort of established. You know, you've seen these glasses, but in terms of the principles of where the color was coming from was debatable. There are various rationales, depends on what you're adding. But this person, Alexei, was trying to basically make various kinds of glasses. And what he did was put copper chloride or cadmium sulfide precursors inside a glass melt. So this is not requiring high instrumentation, fancy instrumentation or vacuum or high temperature or anything like that. This is working in an open beaker on a bench where you're just melting and putting a few sprinkles of a precursor like cadmium sulfide. And this is a paper he published. It was in 1981, as you can see. And the title says it all: Quantum Size Effect in 3-Dimensional Microscopic Semiconductor Crystals. Okay. It's in a journal that was belonging to the Russian Academy of Sciences, and it was behind the Iron Curtain, so very few people read this work outside of Russia. So what do I want to highlight from the data? It does look a little old, so I want you to look at this particular graph here. Let's start with the left side, and this is about the size of the particles that were getting embedded in his glass, okay? And what you're looking at are, on the y-axis is the dimension, and this is in angstroms. So this is, you're looking at very few, these two curves here at 550 and 670, they belong to copper chloride one, and the other one is cadmium sulfide. And you can see that the numbers are very small, and they were, and what happened with that size? He, by the way, measured it through what is called small angle X-ray scattering. What he found is that you can tune the absorption spectrum very nicely. Means that the color of the glass is different depending on the size that he was making. He in fact talks about the fact that it has quantization effects. He talks about the fact that he tries to model it to conventional theory and realizes he is playing with the excitonic band gap associated with these semiconductors, that he's tuning the particle properties, okay? But the problem with his work was it was embedded in glass. You could not extract these particles out of glass, and there's only so many uses you will have with the colored glass that you are forming. Yes, there are quantum size structures inside it. However, they were frozen. So then comes along this person. His name is Louis Bruce. He was working in Bell Labs. He's an American through and through. And his paper that came out very soon after Alexei's paper was 1981, this is 1983, and you can see the title, Size Effects in the Excited Electronic States are Small, and I've highlighted the word colloidal cadmium sulfide crystal. What do I mean by colloidal? Means that it's in a beaker in solution. They are floating in solution, and that was the buzz of it. And because it's synthesis, I want to highlight a little bit about the synthesis that was highlighted in the paper. It's quite impressive. How do you make cadmium sulfide? You take a precursor like cadmium sulfate, you introduce ammonium sulfide, you play with pH, you do it in water, you can make bulk cadmium sulfide right in front of you. The difference that he did was that he added a very large polymer. Now, what does this polymer do? It does not interfere with the inorganic chemistry of making cadmium sulfide, but it creates what is called a capping agent. It's like a jacket that is happening around the growing cadmium sulfide that he's forming. The problem is there's a word that he's used, and I've not highlighted, it's right there. It says slowly injecting the precursor into this. So as he was slowly injecting it inside his solution, there's a jacket of molecules that are going to cap any growing seeds that are forming in his solution, okay? So this lended itself to forming an interesting set of materials. And I'll show you the TM in a second, but this is the size distribution. As you can see, it's not fantastic. He did it in two solvents, acetonitrile and water. And on the x-axis, you can see the dimensions. Again, it's in angstroms, but there's a huge size distribution. So these are not very monodispersed structures. But despite it not being monodispersed, he found that you can manipulate, depending on, if you have a fresh solution, you have an absorption spectrum here. When you age it, the absorption spectrum sort of is not as clean or not as sharp. Means that there's growth of the particle going on. The band gap is changing of the particle. And he was aware of it. He talked about size issues and the fact that these were the kind of TEMs he showed. The problem with Bruce's system was that it was not very effective, but for the first time, he was making very, very small seeds, trapping them in a polymer jacket, and long enough for him to do some measurements, such as TM, which are not fantastic. And these are basically the emission data that he was getting. And you can see there's a shift in the energy, meaning the band gap is getting tuned as you change the size, and it's getting bigger and bigger concurrently. So along comes this person. Now, who is this person? His name is Bovendi, Bovendi. He was actually at one point in 1988 working as a postdoc in Lewis's group. He was working in 1988. 2 years later, he leaves his postdoc position and gets a faculty position at MIT in 1990. And 1993, he publishes this work. All right. So it's a building up on what Bruce had been doing all those years, trying to understand how to grow better and better quantum dots. What did he bring in? And by the way, the title of his paper is Synthesis Characterization of Nearly Monodispersed Semiconductor Crystallites. Okay, and this is the key. And this is the synthesis, but I'll highlight a few things in red. Its contents were delivered vigorously through a stirring reaction, rapid introduction of the reagent, accompanied by a sudden decrease in temperature. Best quality, you control the temperature. These are simple synthetic parameters that chemists have at their beck and call that allow them to tune the quality of the product. All right. This is called a hot injection method. We can go into what is the main principle. The main principle is I again have a capping agent, like a jacket that is going to coat my growing particle, because I don't want it to grow very big. I want to trap it at a 1 nanometer, 2 nanometer level. I have a jacket. What is this jacket? It's a very hydrophobic material called topo. This topo solvent is at a high temperature, and I have to inject my precursors. What I do is I stop heating the topo. It's at a constant temperature. When I introduce new precursors, what will happen? The temperature will drop. This temperature, when it drops, allows these precursors to actually form cadmium sulfide, but because the temperature has dropped, they do not grow anymore. They are trapped. Unless I increase the temperature, they will get kinetic energy, and then the growth will take place. But because the temperature is dropped, they are trapped, and then they are trapped by topo, this sort of organic sheet that comes in, which is simple soft acid-base reaction interaction that sort of is a coating that comes on top of this very tiny seed, which in fact is now a quantum dot. 5 minutes, perfect. So what does his data look like? His data looks like this. These are absorption data, and you can see the dimensions here, 12 angstroms, 16 angstroms. You can tune the size very nicely, depending simply on the heating of that beaker, of his round bottom flask, under very simple conditions. And the quality of his data looks like that. You can change the capping ligand. In that case, it was topo. In this case, there's a selenium, so he's making cadmium selenide, and this is the quality of the suspended colloid. So these are simple ways of making a very valuable material, which ends up having very interesting properties. They are colloids, and because the particle size can be tuned very nicely, each one has a different emission. So what you see there are all the same, they're all cadmium selenide, but with different particle sizes associated with them. What I'm trying to show you here, I'm trying to help you compare of a conventional emissive material, which are organic dyes. A lot of biologists use this for staining, things like rhodamine red, or in this case, it's a protein-based system of DS-Red2. What I want you to see is the line widths associated with it, compared to the emissive line widths of the quantum dot. They're much more narrow, much more tunable. You do not need to change the chemical composition. I do not need to synthesize a brand new molecule to change the emissive properties. I just need to manipulate size. You can do lots of things. So in this case, this is cadmium telluride. I just want to show you a variety of semiconductors that people have played with and can make these beautiful systems that have tunable properties. The quantum efficiency of these materials is fantastic. It's easily 10 to 20 times more than organic dyes. And by the way, you don't have to only work with 3-5 systems. You can work with other semiconductors over time. And in this case, these are all made through the hot injection method. Okay. All the only things you're perturbing are the capping agents. So these polymers that are going and sitting on surface, holding on to the size so that the size does not distribute heterogeneously. You maintain the size very carefully. So there are a variety of capping agents you can use, and you can use a variety of simple synthetic parameters to tune the sizes. So this allowed, in a very cheap way, to make a highly exotic material that has found lots of applications. The first one out of the gate was for bioimaging. Here I'm showing you some cases where people have used quantum dots, functionalized them with various biomolecules, proteins, antigens, antibodies, what have you, to try and look at various kinds of cells and tissues and organs and so forth inside the body. But suffice it to say, these are my last 2 slides. That's not the only thing. Remember, I said one is the optical property, but there's a huge plethora of electronic properties. The way the electron behaves, the exciton in terms of its charge carrier mobility, how bound it is, and so forth in terms of its spin. So people have really found a way now to make these materials very fast. You can in fact buy them from Aldridge, and you can start playing with them. You can make thin films out of them. You can make them 3D printing of these structures so that you can use them for various applications. Okay, so there's a huge plethora. And I'll just leave you with the last slide, which is one application which everyone's familiar with. It's something called, nowadays they call them QEDs, or I don't know, fancy thing. QLEDs and so forth. And so I just thought I will highlight this. This was from May earlier this year, in May 2000. I saw this website, so I thought they said quantum dot displays set to lead. They're going to basically outperform OLED devices simply because of their cost efficiency, quantum efficiency, way of manufacturing, bulk. You can make them in kilogram length scales without any issue. So stop there. So thank you very much.
Thank you, Deepa. That was very energetic, and thank you. We'll take one question, pressing question, if there is any. Okay, if there are none, we will get back. Deepa, thank you.
This is working?
So now, Ravi, you get this extra 1 minute. Yeah.
Okay, so,
Yes.
well, thank you. Please stay until the end. And 20 minutes is a long time in terms of attoseconds, but really short for describing what I'm going to say right now. So, well, go back. That's what we are talking about, and depends on how old you are, how young you are. Thank you, Amit, for this, for all the help with this talk. And so, what are we dealing with here? So, ladies and gentlemen, we are gathered here to make a very big statement about something that is extremely small, in praise of a billionth of a billionth, right? And this is the closest to the impulse, the delta function. If somebody asks you, do you really know what a delta function is? This is what will serve that purpose. So the three people, including a lady, is Pierre Agostini, French and now American, stays in Ohio, but he was at CSACLI for a long time. Hungarian, German, French cross, and Sweden, French, now in Sweden. So, and Lulier. So that takes a bit of effort to pronounce that name, but she has done amazing things. So let me begin with this. So you need to get some basics right. And at the end of it, what they've done is extremely complicated, but we need to know the basics so that we understand what actually they've done. So this is the history of all light pulses, very basics. So we have this Fourier relation between delta and nu, the bandwidth that you have and the time pulse that the duration that you can create. And it's been known for a long, long time. I mean, almost eternal, that we know that this is how things work. And a pulse has lots and lots of colors, right? Much more than the quantum dot colors that you showed. And this is about the contrasting pictures. On the top, you see the pulse, blue, red, and green. And look at them at the bottom. The sharper they are in time, the broader they are in the spectrum, right? And all of us have dispensed with the notion that we are taught in first level courses that lasers are monochromatic. They are not monochromatic at all if you make short pulses of them, right? The shorter it is, the broader it has to be. There's no other option. And a 5 femtosecond pulse, which has been around for about 20 years now in some labs, has a bandwidth as large as 200 nanometers at a central frequency of central wavelength of 800 nanometers. Look at that. It's 1/4 of the center, the carrier wavelength that you have. So lots of frequencies, when they're propagated in a medium, each one has its own refractive index, and so they undergo severe modification when they travel in a medium. And so if you want to know how to make short pulses, so this is a recipe. Take monochromatic waves at many frequencies and superpose them. But don't randomly superpose them in phase. And this is a recurring theme in this entire talk. So superpose them in phase, and this is what is called coherent addition. So when something is in phase, two things are in phase, you say they are in coherence, and so you have to add them. How this happens, it can be controlled from outside, it happens internally inside a medium and so on. But these are all details, but this is the crucial thing that you must keep in mind. So how do you get so many frequencies in the first place? All of us have known lasers, and we know that the laser cavity provides a standing wave condition, because of which it has this comb of frequencies that it generates. Like, so these are all a set of frequencies. They can be infinite number, but only a few of them are meaningful in any particular laser medium where the amplification takes place. So the gap between them is given by inverse of the twice of the length of the cavity. So if you have a long cavity, you have shorter spacing, you have lots of modes in a definite frequency range. If you have a short cavity, you have very few modes. But you need lots and lots of modes. So you take a cavity of the appropriate length. Then the gain medium has to amplify all this, right? All these frequencies have to be amplified, and they have to be amplified and kept in phase in such a manner that you can actually produce a short pulse. So this is an example of how that happens. So you look at the top. So you have all these waves. There's a certain time over a time period at which these things are actually in phase, right? And this is where the so-called temporal interference, or call it whatever you will, that happens, and that produces the pulse, right? Now, if you do the same thing with random phases at the bottom, all you get is noise. This is like a light bulb emission. And so that is certainly not okay for producing a short pulse. And so these pulse lasers, if you take a pulse laser pulse, like femtosecond lasers, we have a dozen of them, more than a dozen of them in TIFR. So if you see the inside, what happens, they have this pulse that is formed, which travels back and forth. Every time it hits one of the mirrors, a little bit of it leaks out. So there's a train of pulses that is formed. And so basically you see them on the oscilloscope, you see lots and lots of pulses, each separated by what is called the round trip time of the cavity. Now, if you look at the spectrum, so for a single pulse, this is how the spectrum looks. But as the pulses keep on building up, you see the spectrum evolves this structure. And again, as I said, equally spaced frequencies, a train of pulses corresponds if you do the Fourier transform, you'll actually see that there are equally spaced, lots and lots of frequencies. And so this is very important. If you take a femtosecond laser and a normalized size cavity, sometimes you have to add thousands and thousands of modes, probably 1 million modes to get the shortest pulse. And the more you add, so this is coherent addition. So you add amplitudes. So the intensity goes as n squared. Amplitudes add as n, intensity goes as n squared, and you get a giant pulse which is localized in time. So, well, why not do this for attoseconds? It's all known for a long time. That's a massive challenge. Why? Look at 100 attoseconds. So that's about 10 to the minus 16 seconds. So it needs a bandwidth of 10 to the plus 16 hertz. And how do you generate coherent waves over such a large bandwidth is a question that is really tough to answer, right? It's been answered, but it was very tough to answer at the beginning. And there is no laser medium. You can't ask for a laser medium. Give me a medium that supports an attosecond pulse. Does it exist? There's no laser cavity that can reflect these pulses and amplify, inside a normal kind of a conventional laser. So enter nonlinear optics, which has been around ever since the laser was born. And strong coherent light produces at one frequencies, produces coherent light at many, many frequencies, right? Variety of processes which give you myriad frequencies. And the beauty is that the input and output frequencies are adjusted in such a way that they are actually in phase, and they travel inside the medium in phase, they exit the medium in phase. And this has resulted in lots of shrinking of pulses even otherwise. In fact, there are many nonlinear processes which can actually give you a shorter pulse than what you have actually put in. Now, if you look at light matter interaction to understand nonlinear optics a little bit, so this is how most of us go through life, saying that, look, there is this electrons inside a medium, nucleus electrons, a light pulse with a certain electric field comes in, creates this kind of a dipole moment, and the dipole moment, so the dipole moment is shown here, separation of charges, and that oscillates, radiates the light, and we have all our absorption, reflection, refraction, everything happening, and that's fine. But when you increase the intensity of the light, and that is correspondingly increase the electric field of the light wave, for example, you take 1 joule in 1 picosecond, which is actually a 1 terawatt pulse. And at TIFR, we have 150 terawatt pulse. So that's a huge amount of peak power. And the electric field depends actually on the peak power focused down to a small spot. So it's a peak intensity that matters for getting the corresponding electric field. So you can go on creating stronger and stronger light fields by compressing light pulses. This has been known again for a long time. So now if you do this, if you put matter in a strong light field, known for decades again, is that apart from the linear term, you have these nonlinear terms, E square, E cube, and so on. And the beauty is that if you put two frequencies, omega 1 and omega 2, in such a medium and excite these nonlinear processes, you can, simple thing is to add those frequencies, coherently add those frequencies and produce a blue light, which is the sum of these two, omega 1 and omega 2. If they are red, and this becomes blue. And the medium, of course, is transparent to both the input waves and the output waves. And you can do this for one atom. And if you have lots of atoms, all those atoms are driven in phase. So they give you a giant signal. You can produce a huge burst of light at the new frequency. So this is very simple explanation. You multiply fields, you actually add frequencies. But the beauty is that you just not add frequencies, and they are emitted in all the directions. Omega 1 plus omega 2 comes only in K1 plus K2. Omega 1 minus K2 minus omega 2 comes only in K1 minus K2. It doesn't go everywhere inside the space. So directed coherent emission from the nonlinear harmonic, the nonlinear polarization that you create inside the medium. So imagine, just for the sake of a few more slides from now, that imagine this as a multiple upward transition and a single downward transitions. Chemists have, in Raman spectroscopy, you have what is called the anti-Stokes emission. There are really no transitions taking place here. This is all imagination because they're all virtual levels, 1, 2, 3, 4 photons adding up and then giving you a giant photon at n times the fundamental photon. And it's not spontaneous, it's not randomly directed, it doesn't go. So I put a big cross there. So please remember that. It doesn't follow. It is a well-directed, coherent, in-phase emission that is driven by the strong light field. So 1 omega can produce n times omega. Fine, many, can produce n minus 1, n minus 2, and so on. Lots of harmonics can be produced. And so in the 60s itself, when the laser was invented in the next 10 years, people produced third, fourth, fifth, any number of harmonics from gases, crystals, and so on. And particularly gases were very popular because of various reasons. They were producing something like, 7th harmonic, 9th harmonic, and so on. But the fields that were available were all from nanosecond pulses. So they were not so large because the time duration was still very large. So they had to wait for ultra short pulses to become common before they kicked up the harmonics. And that kick happened in the mid-80s. It's a paper in Journal of Physics B. One of the first papers, I think it is cited as the first paper. I think it is the first paper where Anne Lullier and her collaborators pushed this light, I'll tell you what intensities and so on, into argon, powerful light, and produced harmonics. So they took the standard Nd:YAG laser light, 1.17 eV, and they at 10 to the 15, 14 watts per centimeter square, they pushed into a gas jet, and where they produced this 21st harmonic. So the highest harmonic from, it made a leap. It reminds me of something that happened in high temperature superconductivity, where things were stuck for a long time at a few Kelvin, and suddenly someone comes and opens it up, and there was a jump of 10, and that gets a Nobel Prize. So indeed, this also gets a Nobel Prize. So this is the first experiment, and then lots of other experiments were done. I'm not going to all of them, but let's just see. What was done was that all this was actually done, and experiments were there. But then nobody understood what was going on. How do you explain this? Because this is not, as you increase the intensity, it's not perturbative anymore. You don't say E square, E cube terms being added endlessly, right? Because at some time the perturbation theory breaks down. So here comes a gentleman, white again, but from Canada, where you come from, NRC, Paul Corkum, and I'm stressing the fact that this guy is an experimentalist, right? He became an experimentalist. He was doing theory earlier, became an experimentalist, and somehow the Nobel citation says it's been given only to experimentalists. And some of that, what I will say in the future, will have some bearing on this. So he came and he made a sense of what was going on, right? He gave what is called the plasma perspective in strong field multiphoton ionization. He not only explained harmonics, he explained several things that were happening around that same time with strong light fields. And he called it, his model, but later it became the simple man's model because any graduate student can understand it. So he sort of cleaned up the entire stuff. And he actually sparked off Attosecond science, in my opinion, and many other people's opinion, including Vaibhav and several others who can vouch for this. So this was 1993, 8,689 citations so far, much more than what most of us can accumulate in one lifetime, right? So one paper just smashed everything, cleaned up the place, and this is what he relied on. He said, look, you have a strong light field. Let's take a 1D atom. And this atom is bound, the electron is bound in a potential like this, Coulomb potential. And now you apply a strong light field. And obviously something funny is going to happen. So the light field is an oscillating electric field. So the light field is actually going to modify this barrier, that one-dimensional barrier, and make a seesaw of this. Sometimes it goes up, sometimes it goes down. When it goes down, the electron can actually find a distorted barrier that it can tunnel through, right? So, and this happens every half cycle. That's very, very crucial, right? This happens every half cycle. And the cycle time, by the way, typically of the lasers that were used were about, like, say, 2 femtosecond or so. So the half cycle is actually 1 femtosecond. And if it is something like 1.5 femtosecond kind of a laser cycle, then it actually goes into the attosecond. It's sub femtosecond. So what did he say? He said, this is what happens. He said, look, initially the laser is ionized by a distorted barrier. And then the laser is taken a long excursion by the light electric field. So it's ionized very rapidly and then taken on a long excursion, returned to the base coherently. It is not randomly. It is returned to the base in phase with the driver, and then it has an option of recombining with the nucleus, with the ion. And when it recombines, if it recombines, then a giant photon is emitted. So you can see here, this is taken out, taken a long excursion, given a lot of energy, goes up there to indicate the energy, and when it recombines, it emits a pulse which is much larger than what was used initially. So what is the energy that's given here? The energy is all this energy, the ionization energy that it takes to get out of this atom, and then the acceleration energy, which can be much larger than, which depends only on the driver field. It depends on the electric field of the laser. So it can give it a large amount of acceleration and then bring it back, and then it drops back into the nucleus more than 5 minutes, right? But please stay on. It gets really interesting, and please apologies in advance for this. So when it drops down, it turns out that this is actually an attosecond pulse. It's an attosecond pulse with a much larger energy spread than what you have given, and so this is called a 3-step model. There's ionization, there's acceleration, and there's a driven recombination back into the nucleus, back into the ion. And the result is an attosecond pulse. So this is a beautiful picture that I picked from one of the articles. So you have this, this distorted potential, and then the electron is taken out, and then you see half cycle later it is returned to the core nucleus, and then it emits this burst of light as an attosecond pulse. So this is really the story of the attosecond burst. How it forms an attosecond burst, I will try and hint why that happens. But actually, for a long time, people were saying high harmonics are produced, because there was no way to measure these high harmonics. Short pulses are very difficult to measure. They need special techniques called correlation of one pulse with the other, and so on and so forth. This is a matter of detail and can be quite complex. The simple principle is that you overlap 2 pulses and look for, it's actually what I call an eclipsing method. You take one pulse and you take another pulse that passes through this pulse, and when the overlap is maximum, the extent of the pulse itself defines the overlap. And when the overlap is maximum, or depending on the overlap between the pulse, one pulse which is a reference and another pulse which is traversing, you can get a signal which is a peak signal, and from there you estimate the duration of the pulse. It's called correlation, autocorrelation, cross correlation, various things. So Agostini, who is listed as the prize winner, published a paper in 2001, his group, still I think this was C.A. Sackley, where he said that, oh, these harmonics are pulses of something like 250 attoseconds, right? So that is the first good measurement of these pulses. And then Ferenc Krauss, the third winner, came and he said, oh yes, around the same time, oh, you have 250 attoseconds, I also produced 650 attoseconds, but they were nearly simultaneous. So I think the credit goes to both of them. So this paper is titled Attosecond Metrology. Look at the beautiful title. It says everything, in just 2 words. It's lovely to have such small, short titles. So people then said, oh, but still, their electron fall is not really controlled. So maybe you're not producing a single pulse, but you're producing lots of attosecond pulses. There's a burst of attosecond pulses. So then somebody said, oh, shrink the pulse so that you get only 1 attosecond pulse. What do you mean by shrinking the pulse? If you have a reasonably long pulse, that actually produces a burst of attosecond pulses. Every time the sufficiently strong electric field of the light drives the ion with enough energy back into the core, and then you get an attosecond pulse. But if you have, look at this pulse. How many can you count? This you can count lots of cycles, 1, 2, 3, 4, 5, 6, 7, like that, right? And here you can count 1 and 2, barely 2.5 cycles, right? So this is a very short pulse, and the interaction happens essentially at the center, lovely. And then you get an attosecond burst that's emitted. So period. So you have one single attosecond pulse. So you take a 5 femtosecond pulse or a 4 femtosecond pulse, you can get a single attosecond pulse. There are other ways of, sort of slicing and so on and so forth, but we don't get into those here. So what use are these, right? So why are we excited about attoseconds? Because we know that inside the atom, the electron motion is all in attoseconds. Very often I ask students in my class, all of you know the lifetime of an excited state. You say, oh wow, 1s state has, or 2p state has nanoseconds. Why? Oh, it comes down spontaneously in that time. I measure this, I get an e power minus t by tau, and that's what his lifetime is defined. I turn the question and ask, how long does it take to go up? They say, oh, instantaneous. Instantaneous is not an answer. How short is something that we can't measure, but we couldn't measure till now. Now we know that it takes attoseconds to go up. And to know really that attoseconds is taken, that's what it takes. You need a pulse that's actually shorter than that to make a measurement of these kind of things. So photoelectric effect is now being revisited by experiments where they took this neon 2p2s photo emission. Now, so they were trying to say whether the electrons in deeper levels or more tightly bound levels take more time to get out of something that is tied loosely to the nucleus. And they find a delay of, the details you can read in this paper, it says 21 attosecond delay between the ejection of an electron from one of these states to the other state. So there's 21 attoseconds. So it is not instantaneous at all, right? So we should forget instantaneous as an answer for this. And this is a very complicated study. Just the results is what I'm presenting. It's again by doing what is called the photoionization measurements and lots of cross calibrations and so on. So this is what is truly the atomic era that's happening now. And now electron tunneling. In fact, there's really when I read about tunneling, I knew that there were lots of tunneling times. How long does it take a particle to tunnel through a barrier? There's several theories about. There's a Landau tunneling time. There's a Whittaker tunneling time. There's a Wigner delay that happens. Mind-boggling. But now we will check out who is correct and who is not by doing what is called the tunneling process itself. And Carlo is not here, but he loves this, probing electron dynamics in solids using high harmonics. So he uses helium lamp of 48 electron volts. We can give him a variety of, choose any EV that you want, up to 100, 200, 300 EV, whatever you want, we can give you. So these kind of things are becoming popular. And the story is just beginning. In fact, I've just taken 2 examples. There have been some 10 fascinating experiments in all aspects of the ultra-rapid motion inside atoms and solids. Now, closer to me is that we are having a petawatt laser soon in Hyderabad. TIFR will be proud possessor of this. 30 joules in 30 femtoseconds is 1 petawatt. Now, 30 joules in 30 attoseconds will be 1 exawatt, right? So you want anyone ready to buy this? So soon we may have it actually as a pulse. And so I'll take 5 more minutes. There's an interesting part. So please bear with me. There's a quiz for you, right? So that you can talk intelligently about attoseconds. No, but this is important. So scientific profiles. So please stay on and please shut the door there. So Agostini, 95 publications, H-index 35. Cross, 6,213 publications, H-index of 181, right? So imagine, that means Cross has done much more than attoseconds. He's in so many fields, I can't even count what all he has done. Tremendously productive. Hey, what happened?
Audio.
Yeah, audio. Please, can you share it again? I have an interesting audio. Can you share it again?
No, I thought it was a good time keeping it.
No. Please do not leave because there is something very exciting that's about to come. Yeah. So please share the audio and please give me this. Please share the audio. Now, are we all set?
Yes.
Good. Okay. So this is Krauss and then Corkum. Where's Corkum? You have not, shall I push this or? Okay. So, but yeah.
Okay.
No, we have gone behind.
Yeah, now you know.
And Lullier is 172.59. and then Corkum. Look at 86924938 36412. Wow, wow, wow. 1,000 above, 10 papers with more than 1,000 citations. He is really the man who said attosecond physics. Really the guy who should have been there. But alas, he's not there. And incidentally, the Wolf Prize, which is a precursor to the Nobel, recognized Lullier, Cross, Corkum right there in the middle. Right? We expected the same, but it was not to be. And now Cross has done lots and lots of things. So this cross encounters of the Atto-kind, he's promoting ultra short science in blooming, pulses are blooming in the desert and so on, Saudi Arabia. Then rapid fire round for you. Can we make an attosecond laser in a simple box? Right? Anyone? The answer is no. Okay, there are no media, right? Okay, a femtosecond laser takes a lot of effort to generate an attosecond pulse right now. Perhaps in the future, you will have one. What is the broadest bandwidth coherent light known so far? Attosecond pulse, right? How high a harmonic do we have now? Unbelievable numbers, beating, matching Corkum in some of his citations. We can actually go till thousands. The harmonics the order can go into the 1,000th range. So from EV, we can generate a kilo electron volt coherent radiation. This is truly the coherent X-ray pulse that you can generate, because other X-ray lasers are all spontaneous emission, amplified spontaneous emission lasers, which are not really true lasers in my opinion. And can an attosecond pulse excite valence transitions as most of us normally do with normal light pulses? Well, it can, but it also excites deep transitions, VUV and X-ray regions, because it's got 60 EV, 100 EV, 200 EV like that, right? So it combines lots and lots of states, creates a wonderful wave packet that you can see evolution as you move. And now, so this is really you will see there's a connection to Shiraz, who's sitting here. Well, I'm glad you're here, Shiraz. So, chaliye KBC khelte hain, right? So, what is the shortest light pulse ever produced? Options hai 30 attosecond, 43 attosecond, 130 attosecond, 153 attosecond. This poor guy has no clue. So he's scratching his head, the timer. Well, at this rate, this is a 1 crore question. Okay, it's very tough. So he says, I like a lifeline. ठीक है, किसे फोन करना चाहिए? So the answer is Sheldon Cooper from California. How a guy like this knows Sheldon Cooper is a mystery, right? And why he chose Sheldon Cooper is with knowledge. I'll show you how. So he says, computer G, Sheldon Cooper ko phone lagaya jaye. So there it is. So, and Sheldon Cooper, by the way.
First question is on the topic of optics. What is the shortest light pulse ever produced? Dr. Cooper.
And of course, the answer is 130 attoseconds.
That is correct.
String theory is no more than string theory alone. And they think that they know everything, by the way, which is probably also true. But now, what do you expect? So this guy gets 1 crore and goes home, right? So what a happy ending. 1 crore, what you expect? Afsos, galat jawab. He is marked 130 attoseconds, but ठीक है, अगर आप कुछ नहीं जीते आज, अफसोस है कि आपको 3,20,000 में जाना पड़ रहा है, घर में घुसने नहीं देंगे. लेकिन अगर आप guess करेंगे तो क्या करेंगे? He can't guess. He says the correct answer is 43 attosecond as of now, right? This is from the group in Zurich, Jacob Wormer and co, where several TIFR people are doing postdocs. So that is the power of attosecond pulses. They are so popular, and everybody wants to have, wants to know what they are. And this is a Guinness Book record. So for, people say this is a standard slide, 1 attosecond and 1 heartbeat is 1 second, and 1 attosecond is to 1 second what 1 second is to the age of the universe. It's a very popular thing that is said. You can have your own take on this. But my point is that no wonder for such path-breaking advances, होना ही था. Okay. So, well, you concluded, but I'm just going to say just one more short thing. The femtosecond pulses have been storming the Nobels for a long time. 2005, November 9th, one day later, I had the pleasure of summarizing this. 2018, October 24, 2 weeks earlier, I had the pleasure of summarizing something that is close to our own lab. And please, did anybody recognize the significance of this? The Nobel 2023 in physics is correlated with the Nobel 2016 in literature. Bob Dylan, who said the times they are changing, right, wrote this, and he was given the Nobel Prize for several of the things that he did. And whether it's music or attoseconds, what matters is in phase. Repeat that: in phase, in phase, in phase, right? And then you have great things happening. So this is a real thank you. Thank you.
Thank you. So we would like to request all the three speakers to come up stage back again. Thank you, Ravi. That was so much fun. Okay, so back to some of the questions. We would like to take questions. So first, let's ask a pressing question to Ravi. Questions for Ravi? Aha, a biologist, and then okay, first.
Okay.
So thank you for an amazing show. What do you actually do with attosecond pulses?
Okay. So I hinted at two examples. One is to study the dynamics inside the atom. You know, inside molecules, we have been studying dynamics for a long time, saying that they vibrate on hundreds of femtosecond time scales. You can catch them vibrating. Inside crystals, ions are oscillating on picosecond or hundreds of femtosecond kind of vibration time scales. So now you can catch, if you can imagine an electron cloud changing its shape inside an atom, you can capture that. That is the hope. And the other thing is that you can probably, people are also saying that you can have very rapid electronic devices, because now the time has been reduced to attoseconds. You can clock attoseconds. So maybe you can make devices which are much faster. And so there are several things which are being sort of dreamt about right now. I'm sure they'll all be reality very soon. Yeah.
Okay. Question for Deepa and then Amitesh. Any pressing question for Deepa? Okay. Yes.
More a comment for the question. Yeah. I think you missed something. There is a vapor phase condensation. The one that is used for C60, for example, has been used a lot since 77 when I was a postdoc for actually looking at quantum dots, and quantum size effects were known even then.
Obviously, they've been known for a long time.
Okay.
Vapor phase deposition of
Vapor phase condensation, just like for C60, same kind of thing. The cluster people have been doing it for a long time. And from clusters to getting to solid state kind of things has been known for very, very long.
Fair enough.
The second thing is the glass crystals, nanocrystals. At least in 1932, they were characterized by X-rays.
That is not an issue. In fact, the Nobel Committee sort of wrote an article in terms of characterizing is one thing, but in terms of explaining and correlating it with the theory. No, but in terms of, in the same article, having the accountability for the observations. Many people have observed these things. Many people have used the word, oh, it's an anomaly or something along those. So maybe I am not fair enough if those were there beforehand, but these were the ones that the Academy highlighted.
Second question that I want to
Yeah, you can put the mic up there.
Yeah. Was that actually quantum dots from the semiconductor people, quantum size effects were known for very, very long.
Right.
Okay. There has not been any issue on that. And the devices that the real thing that the chemists have done is that they have extended it to sensors, which are much more important, which would not have been easy for the solid state lights.
Oh, absolutely. I think maybe I didn't highlight this enough. It was simply the synthesis of these materials, the fact that you can adapt them to large scale, to kilogram scale, for example, which conventional approach that was being used beforehand did not allow such easy, facile, low cost, large scaling. This is the beauty of the work that these guys did. Yeah.
Right. I want to restate this, that if you can make something in your lab doesn't mean it scales up to industrial preparation. So you have to have the same scaling factor to make the material, and it requires a little bit of a change in preparation. Okay, question for Amitesh. Yes.
Amitesh, so you mentioned that the way this immunogenic response was, they overcame it, was that they changed the nucleosides, right?
That's what I was trying to draw.
Yeah, you were trying to draw that. So the bacterial nucleosides are different from the human one, mammalian ones. The modifications are different. But what about the viral one? So they also they must have to change that when you're doing it, right?
So these base nuclear modifications are directly correlated to their evolutionary history. So the more advanced they are, the more nucleoside modification are there. So viruses probably don't have that much of them.
So in the case of the mRNA vaccines for the viral infections, they did not have to make those changes.
Yes, they have to. So in fact, the mRNA vaccine that's developed both by Moderna and BioNTech, Pfizer, both have this thing, pseudo-uridine, this exactly.
Okay, so and then they change it to uridine. That's it, right? Or
sorry,
so
uridine gets converted. Uridine get replaced by pseudo-uridine.
Okay, so then in the vaccines, you have to the mRNA for the
in the vaccine you have to have the modified one, because the modified one is the one that triggers lesser immune response.
Okay.
Okay. More questions for all the three? Anyone? Yeah. Yes. Maybe we can pass on it. And the Zoom one. Yeah.
Yeah. Question for Ravi.
Okay.
So, I was just wondering, nonlinearities played a very important role in what you described. So, in non-physics, so there's this story of solitons.
Yeah.
Yeah. Okay. And so classically, you have solitary waves which go without distortion for a long time. And so theoretically, certainly you can construct models of solitons which correspond to very short energy densities propagating without distortion. So I was just wondering whether, such things have been used to create very short pulses.
Yeah, in fact, somebody tried to make a soliton laser too. Soliton being that, nonlinearities, particularly in fibers. The nonlinearities, they are, once you launch a pulse through a fiber, nonlinearities were a very serious problem initially. Like they used to say that, they stimulated Raman scattering and all sorts of things were happening.
Right.
But the Bell Labs people, Molinar and other people, I think Kailash probably knows more about this. They actually said that, soliton formation happens when there are two competing things. There's something trying to diverge you and there's something trying to put you back. So when there's a balance between the nonlinearity and the normal dispersion or diffraction, it can happen in space or in time. So people have produced solitons in several contexts in nonlinear optics. And they've been measured, they've been seen. So I can give you some. Something. Yeah. It can't be.
Of course. Yes.
Only it doesn't change its shape as it propagates and remains further spread of the wave. Pulse doesn't happen once it's formed. Yeah.
Thank you.
Questions from the Zoom audience? There were actually 40 odd participants. Is there any question from the Zoom audience? Anybody would like to ask a question? If not, is there any pressing?
Yes. You said the 40th harmonics. What is the efficiency of that? Means
40th.
Yeah.
So, well, I did not get into the details. The efficiency depends on what you are actually using, right? So the curve goes like this. Initially, the harmonics drop off very rapidly in power, but then there's a flat portion followed by a rapid cutoff. So simple question, from gases, efficiencies of 10 to the -5, -6, -8 have been used, but then you're driving with such a large power that you can get still very useful light at the high nth kernel. If you use this on a solid now, people are saying that you can get 10 to the minus 2, 10 to the minus 3 kind of efficiency, but that needs a special condition and much higher powers than gases. So the efficiencies are, in fact, these are being used in the labs for doing various experiments. So easy, not a problem.
Okay. Well, let's have a big round of applause for all the three presenters. Fantastic show, all of three. Thank you very much that you did that for all of us. So we'll have some snacks outside the West Canteen. So thank you. And I would like to thank the AV staff in the auditorium. So thank you.